Hello and welcome everyone to today's conference session, Achieve Fame, Flexible Automated Machining Efficiency. I'm Michelle Jacobson, the Assistant Editor of GIE Media Manufacturing Group of Publications. Today's medical developments, today's motor vehicles, today's e-mobility, and aerospace manufacturing and design. I'm excited to introduce our speaker today, Dan Skulan, General Manager of Industrial Metrology at Renishaw. Dan helps companies increase production throughput, maximize flexibility, and ensure optimal part quality in precision metal manufacturing, both CNC and metal additive. Backed by a global team of industry experts, he works consultatively with companies who wish to achieve higher levels of productivity while reducing costs. Dan holds degrees in electronics technology, industrial manufacturing, and marketing, and has over 35 years practical experience with manufacturing process evaluation, design and control as a user, integrator, and supplier. He is currently the marketing chair for the Association of Metal Additive Manufacturing and is the industry development board representative to the metal powdered industries. Before we dive into his presentation, I want to remind everyone that there will be a Q&A session at the end, so please feel free to submit any questions you have at any point during the presentation by submitting them in the Q&A icon in the control panel. We'll get to as many of these as possible. With that, I'd like to go ahead and turn things over to start the discussion. Dan, the floor is all yours.
Michelle, thank you very much for that kind introduction. And I want to welcome everyone here to this presentation. I hope to share some information over the next 45 minutes that will be beneficial to everyone watching here today. The title of this presentation, Achieving Fame, was selected. We'll explain what that's about. Let's just start with the agenda. So first off, we're going to talk about manufacturing, a crisis that we have right now that will explain why we use the term fame. And from there, we're going to talk about some of the imperatives of fame. So taking control of machine accuracy, automated setting operations, controlling processes at the source, optimizing inspection functions. And then we'll leave some time in the end for questions and answers. But I'd like to get right into the big picture of why we're talking here today. So first off, if you look at your screen, what you're looking at is the number of jobs that are available in the United States in manufacturing historically, and then also projections from the Bureau of Labor Statistics. You can see that even without COVID, in and around 2019, 2020, the estimate was the number of jobs, the number of people, places of employment for manufacturing was going to decline. And the number of people available to fill these jobs is also declining. So the industry itself has a shortage of jobs and a shortage of manpower to fill the jobs that are there. So we have a challenge taking place when it comes to jobs and people to fill those jobs. But with COVID-19, this changed even more dramatically. We were seeing people prior to COVID starting to automate, trying to replace aging workers and skills that were going away. But with COVID and shutdowns and social distancing and things that are going on, we saw a sharp decline in the number of manufacturing jobs that are available. And in fact, the estimates are that many of those jobs will not come back. They're simply going to have to be filled with other methods, automation and the like. The interesting thing, though, is on the backdrop of the diminishing market for jobs and number of people available for those jobs, the manufacturing output of this country has continued to increase, with the exception of a couple of blips from a recessionary period, COVID itself. The trend has been up for the last 30 years, and the Bureau of Labor Statistics and the Federal Reserve both estimate that that will continue for the next 10 years or more going out. So if you look at those together, you see that we have an interesting phenomena. We have a output that's continuing to increase, and we have a shortage of jobs and a shortage of people to fill the jobs that are actually there. And that gap requires fame. So what is fame? So fame is, first of all, flexibility. So we want to be able to respond to changes in product designs rapidly and at a low cost. You take a look at the automotive industry. It used to be that you could build a 8-cylinder engine and put it in 20 models of cars, and they would run for 10, 15, 20 years production of those engines. Now, by the time an engine is released, a new version is already in design and ready to be launched for sale, whether it be a hybrid or full electric. So companies have to be flexible in order to capitalize on this opportunity. Automation. So automation is the use of technology to execute recurring tasks and processes where manual effort can be replaced. So we simply can't afford to have people doing things that can be done by machines. We don't have the people, and quite frankly, we can't afford to have as many people as we traditionally had. So automation is a necessity for people to succeed in this environment. And efficiency. We have to be able to produce a maximum output with minimum wasted resources. So scrap and rework, extra time, processing, moving parts around in factories and things like that, that simply has to be avoided for people to succeed. So I speak very passionately about this industry. I'm honored to be able to go into some of the best companies in the world and work with them. And I see some remarkable things taking place in industry and companies that are going to definitely succeed. I also see things that aren't moving forward in a lot of companies, and I'm concerned about the longevity of those companies. So what I hope to share with everyone today is some of the things that you take away from the very best of the best companies that you can use to capitalize on the opportunity of increasing manufacturing output, but a shortage of manpower and the inability to use people in a lot of locations, a lot of cases. So the other definition of fame, other than flexible automated manufacturing efficiency, is being known for notable achievements. So this is the beginning of a series that I plan on conducting through 2021, where we will be interviewing experts, many of the people that we know, and pointing out some of the things that they have done in their companies that help you to capitalize on the increased manufacturing output, but do it in a very cost-effective, low human labor way. So I try to throw in some notable quotes. So Albert Einstein said, who is somebody, German physicist, developed the theory of relativity, was forced out of Germany, came over here and lived a wonderful, productive life. In the middle of difficulty lies opportunity. So let's seize this opportunity together. So first off, we have some imperatives. If you're going to succeed and you want to really thrive in this environment, I'm going to lay out 4 things that successful companies do and that I encourage everyone to take advantage of to be successful going forward. First off, establishing machine accuracy. Let's not be mistaken, we're talking about metal cutting operations here, and we want to establish the machine accuracy. So first off, whenever a new machine is installed or a machine is moved, it needs to be calibrated. We're blessed in this day and age with machine tools that have the ability to be compensated using various tools and products out there, laser calibration systems being the foremost, but calibrated so that we know what the precision is of the machine. So calibrating the machine upon installation is a must. But the next thing is machines don't necessarily have optimum performance from the OEM. It's very common, Renishaw, while we produce a lot of metrology products, we are a machine shop and a high volume productive machine shop. Small batch sizes, but in high volume production per year. And we commonly tune machines, and we have many companies that we work with that tune machines to get 75, 100% better performance out of a machine for their particular application over what the OEM specifies when it comes in. So calibrate on installation, optimize the performance of the machine. Verify that before cutting every time. Before you start cutting, make sure that the machine condition has not changed. Evaluate trends. Make sure you're monitoring the trends in the machine capability, and that allows you to repair the machine, tune or physically repair the machine before those trends, the movement away from the accuracy that was calibrated, affect your production. So those steps need to be followed. They're absolutely critical as a foundation. So one of the tools, and probably if you take nothing from this presentation but this, get a ball bar. If you have CNC machines and you don't have a ball bar, and this is not a sales pitch for Renishaw, this is simply the best diagnostic device available. It's a simple 15-minute test, goes on any type of 2 to 5 axis machine. benchmarks the machine capability. So you've tuned the machine, it's installed by the OEM, or you've installed it yourself and you've calibrated this machine. This benchmarks it and gives you a number that tells you what the performance accuracy, positioning accuracy of that machine is volumetrically. It provides data that you can use to tune the machine, and it also identifies error sources if something is out of tune. The key thing here is using this on a periodic basis on your machinery allows you to monitor trends, and you can set tolerance bands on those based on your part tolerances. So you know in advance if a machine is drifting toward the area where it can't produce a good part. This allows you to schedule your maintenance around in advance of producing bad parts. So no more firefighting on the machines. Have to get away from that. Simply don't have the manpower to do it. We have a lot of product we have to get out the door. So once we do those tests on a regular basis, we need to have the way to validate the performance of the machine right before cutting. And the way to do that is with a probing system. Here we're showing a scanning probe, a Renishaw Sprint system with an artifact. We have a precision sphere, and we also have a cup, a tapered cup. So on the sphere, when we scan it, we can simulate the same measurements that we got on our periodic ball bar test. And we look at just the form variation. We don't have all the diagnostic data that we would have on a ball bar. It's not required. We're just seeing whether things change. So we look at that form value, that's stored as a variable on the machine, and from there it can be processed. You can take action. If it's good, we move on. If it's not, pull out your ball bar, diagnose, and see what's going on in the machine prior to moving forward. The next step on the same thing, and again, this is all, you notice you don't see any hands on this. This is all done automatically. We're evaluating the centers of rotation. So when we are dealing with fourth and fifth axis, many of you are dealing with now on these machines, knowing where those rotary axes are in space is critical. All of your CAD drawings, all of your CAM programs are assuming that this machine is perfect. And I can tell you, it's not. There's no such thing as a perfect machine. And a brand new machine calibrated by the best OEM may have thousandths of an inch of error in the centers of rotation, which will turn into scrap in a heartbeat. But by checking this right before the use, and you can take the information about that centers of rotation, store it in the control, and even update parameters on the fly so that machine at that point in time is accurate. We now know the volumetric performance because we based it on our ball bar test. We know the centers of rotation. This is all critical, and this can be done completely automatically. So what are some of the benefits that we get or the results that we get from establishing machine accuracy? First of all, you can put any work on any machine. No more choosing which machine is tight enough tolerances, chasing things around, oh, I got to use that on this machine over here because that holds a tighter tolerance. No, every machine capability is known. You can put any work on any machine, giving you ultimate flexibility. Automation, this is critical to automation. If you don't have a machine, if you don't know what the positioning capability is of your machine, you have no business cutting on it. You certainly have no business automating the cutting on it. You have to understand what the capability of the machine is to be successful. And then efficiency, freeing up engineering time. I can't tell you how many times I go into companies with poor performance who have engineers walking all over, updating offsets on machines because the machine is not capable fundamentally of producing a good part. And they're chasing all around and they're wondering why they have scrap and rework. And they fundamentally don't know. I could ask that same customer, why are you having this problem? And do you have an understanding of your machine capability? And they don't have a clue. So companies that succeed take control of the machine accuracy, and it's not the OEM, they do it yourself and make sure that you understand what's going on with every one of your machines, and you'll free up considerable engineering time. So Kelvin, who obviously invented the Kelvin system of absolute temperature measurement, if you cannot measure it, you cannot improve it. And we start with that there on this foundation. So the next imperative is we have to automate the setting operations. We now have a calibrated machine. We know how well the machine can perform. We want to automate the setup of that machine. So first off, these are the critical steps. So you can, on the machine without an operator, and these are things that an operator typically would do, and some of them, like this first one, are actually overlooked in a lot of automation. We need to make sure we don't overlook when we're doing automation what an operator actually would do. So the first thing is it the correct part? Is it the correct raw material going in the machine? Simple check can tell you that. Then, are we calling up the correct program? So we can validate, we can call it directly or just verify that the program does match the part that's in the machine at that time. Then we set work offsets on the machine. Where is that part located within the machining volume of the machine? So typical work offsets, but we can also do coordinate rotation. How is the part aligned to the machine axis? This can all be done automatically. So then after we have the part set adequately on the machine, we set the tools. So all of this can be done automatically. To demonstrate this, I'll show you inside of Renishaw's own manufacturing. So here we have raw material loaded in the machine. A probe comes down and checking an artifact, we're verifying that the machine calibration is still good prior to cutting. We talked about that in the last step. We want to make sure we verify it. Then we use a probe, we validate what the part is and pull up, make sure we have the right program running. And then we do a setting of the work offsets automatically. Then the tools are introduced in, and each one of the tools are set automatically on the machine while the tool rotates. And setting a tool on a machine gives you much tighter precision than offline presetters because it takes into consideration the error of the spindle rotation and run out of the tool itself. And after we do that, we can actually commence cutting on the machine, and we know that that machine is capable of producing that part, and the part will come out good. So what are the results that we see from automating setting operations? So any operator on any machine. So before we said any work on any machine, now it doesn't really matter. The skill set that's required to push a green button on a machine and make sure that the program executes through is something that can be shared on any machine out there. So we want to get these operations down to where the door is closed and a button is pressed and everything runs from there. So we eliminate manual setup. One, it's dangerous for people to be leaning in machines. I can tell right away whether a company is going to be successful when I walk through doing an assessment. If I see people leaning in a machine, I know that company has a problem. There's no reason for an operator ever to be that close to the spindle of a machine in setup. But you're eliminating all of the manual work that's done. And there's a tremendous amount of manual work. It's not uncommon for a company to take setup time down from hours to minutes. And that frees up, that gives you more and more capability going forward. So efficiency, eliminating human mistakes. National Machine Tool Builders, about 10 years ago, did an assessment of the cause of scrap and rework in machining operations. 55% of all scrap and rework was caused by the manual keying in of data in a CNC control. 55%. So if you do this, you can expect to cut your scrap rate in half right off the bat. And that's not looking at anything else other than just the mistakes made by somebody entering a number into a control. So Henry Ford, who really moved forward the automated manufacturing, production lines, and being able to mass produce vehicles. If you always do what you always did, you always get what you've always got. So you know what? Now's the time to break out of it. We had a lot of companies that were looking at automating and dabbling into it. Oh, is it cost effective or not? COVID has accelerated that considerably. Companies who don't automate and replace the manual work that was done by operators are probably not going to be in business in the next 5 to 10 years. That has to happen, and it has to happen now. And it's very cost effective to do it. So there's really no reason for people to not move forward with that aspect. So those are some of the results you get from automated setting. So the next imperative, FAME imperative number 3, is controlling processes at the source. So if we look at this, the critical steps here, when you are wanting to control a process, we don't need to measure everything on that part. We do need to measure, but we want to measure single features. Really, you measure the tightest tolerance feature produced by each tool. So if you're using 6 tools in a cutting operation, you pick a feature that's produced by each one of those tools that has the tightest tolerance, and you measure 6 points. That's it. You want to measure just what you need to measure. And you provide direct feedback into the process. So the process now can control itself for variation that occurs from the part, from the tool, in the environment. You can also, after the cutting is done, check for broken tools to make sure the next time a part is introduced in there with that tool, you're not cutting that and setting yourselves up for a crash and major problems down the road on the machine. So you can validate the surface condition. So maybe the tool is still cutting to size, but the surface condition, that waviness and surface finish is off. And that's a pre-indicator of the breakdown of a tool. So we're looking at things that we can use to control a process and control things prior to producing any scrap. And then real key important here in this Industry 4.0 age is we want to take that process data and bring it out to be able to monitor it remotely, see exactly what's going on these machines as we are cutting in process. So I'm going to show a video here. And one of the really key things that effective companies do is adaptive machining. So this is a concept called cut, measure, cut. And many aerospace companies have been doing this for 20 years because they're working with extremely expensive parts and they really can't afford to have any scrap or rework. But it isn't just the high dollar value companies that benefit from this. As the measurement sequences get faster and faster on parts, it's critical, and I'm going to play that again here. It's critical that we be able to control the process in real time. So we're facing off this part, we're cutting a feature, and then we're having our probe come out and we're measuring. Then we apply the effective measurement size to that tool for a final pass to bring it into size. Now, remember, we are starting with the premise that our machine accuracy is well known. And before we put the workpiece in the machine, we are validating that the machine is still in very good condition, correct? So there's really no reason why we can't use this machine to control itself in process. We're able to, with this type of operation, many companies are able to hold tolerances down in the tenths, 3, 4, 5 tenths, commonplace using this type of technique. Open-ended machining, where you just machine without this type of technique, it can be very difficult to hold tolerances twice that amount. So let's say you don't have the time, or for some reason you're restricted on being able to measure in the machine, then the next best thing is to measure directly by the machine. Here we're showing a robotic system using an equator, which is a programmable gauge, sits right by the machine and can be directly interfaced with the cutting machine. So we measure the part coming out of the machine, and we monitor the results. And we can look and see if we start to see a drift in the process, we can take the information that we get and feed that information back into the control, similar to what we just did with the probe prior to that in the machine. But here we're doing it right near side, right next to the machine as we're cutting. So the feedback goes in, and after the feedback goes in, on the next pass, we see that we've brought the accuracy of this machine right back down to nominal. Now, in practice, what you'll do here, depending upon the cycle time and the part frequency, is you'll apply maybe a portion of that. We don't necessarily apply 100% correction. So sometimes there's averaging that takes place to make sure that we keep the process stable. But the bottom line is here, we're taking the measurement, we're bringing the measurement directly by the side in the machine or by the side of the machine. We're measuring real time every part, only critical features, 1 feature per tool, tightest tolerance per tool. And we're taking that information and we're setting tolerance bands on it that are inside what the dimensional tolerances are for an acceptable part. So we're using this for process control, feeding that information back into the process and controlling it, bringing it back in line automatically. With this type of technique is incredibly beneficial. So if we look at it, what are some of the results that we get from controlling the process at the source? So first off, flexibility. So depending upon the type of material that comes in there, and I need to stop on here for a second because we have billet. We have material that's just cut a chunk of billet and it's turned. We have castings. So with castings, we have core shift. We have different things that occur to where the casting changes in its size and form. And if we set up a program to be able to handle any size and form without actually measuring it, we end up wasting a lot of time doing open air cutting and things like that. So by using this type of system, we can allow the machine to adapt to different material. different tooling as the tool wears. We can directly compensate for it during the process, but also environmental changes in temperature of the environment, the temperature of the workpiece, temperature of the machine tool itself. Because when we measure directly at the point of contact of the part, all of those changes that take place in the environment, the tool, and the material are factored in. That's where the rubber meets the road. So on this one, though, with flexibility, there is an increasing move toward using 3D printed materials coming into metal cutting operations. This is very critical to have this type of process control for 3D printed parts because they all require some level of machining. Surface finish coming off of any of the current industry's 3D printers is not such that it can be mated up with other parts in a functional application. So there's machining that always takes place, but there's very little excess stock. So it's a near net shape. And not only that, the part going in, if you have a billet, you have $30 and a chunk of aluminum going into the machine, big deal. If you have a part that's been printed for 100 hours on a metal printer that has all kinds of complex internal structures, and you're doing a final pass for a mating face of this part, you can blow thousands, not tens of thousands of dollars by not using this type of automated approach for process control. So automation, we are replacing, in this case, the human oversight. So in the setting, we're replacing manual operations. That stuff can be done by the machine, no problem at all. We need to make sure we understand all of the different steps going in. But here we're looking at oversight. This is where we have people that have knowledge of what's going on that are making decisions. So a lot of the things that we're doing with process control here are replacing the brains or taking the brains of your manufacturing engineers and duplicating them out in the machines. This is very critical. I've seen a number of companies have departments, manufacturing and engineering departments that have been cut to a quarter, a fifth, a tenth of what they were 10 years ago, and yet they still have to produce a higher output than they did in the past. So these engineers simply don't have the time to go and babysit these machines, make slight variations and adjustments. The machine has to have that control embedded in it, and you can't teach the machine to do it. So using your own manufacturing capability and experience, teaching the machine to be able to have that oversight. So efficiency. So this is very key. Waiting for quality control to get back to a machine to tell you if it's good or not, so you can make adjustments to the process, is one of the biggest wastes you can see in manufacturing. And yet it occurs consistently. We have machines out on the floor. We have labs with CMMs. Parts come off the machine. They wait in queue. They soak temperature. They wait for the operators to get through the last batch of parts. And then the QC person comes out on the floor and tells the operator, hey, the part you made 17 parts ago had 3 thou of error on it. Now you have 17 parts that are scrap or need to be reworked. And you lost all that efficiency. Grossly inefficient way to control a process is to measure a part on a CMM in a lab and get feedback manually through word of mouth from the QC guy to the person, or guy or gal, to the person out on the machine. So no more waiting for QC feedback. That feedback instantaneous. And again, we know our machine's calibrated and we verified it right before we cut this part. There's no reason why we shouldn't trust this to provide the direct feedback to control the process. So Edward Deming, sure way to increase productivity is to better administrate man and machine. So we are in no way advocating for the demise of people in manufacturing. In fact, there's bright careers for people in manufacturing, smart people who understand how processes work, that can direct and manage these intelligent systems that do the controlling of the setting and controlling of a process automatically. So we need to better administrate that. The times of having an engineer stand by a machine and dial in numbers based on verbal feedback from somebody at a QC lab, those times are over. And companies who continue to do that are going to have a very difficult time going forward. So we need to maximize the effectiveness of the people we have. We need to multiply their capability out through the shop, providing these tools, in-process tools, and having the smart manufacturing engineering people that do exist all over the place, administer those and manage those tools so we can multiply them. You can get by with a few really smart people and a bunch of highly tricked out machines basically doing the work. So it's really important that we balance man and the machine. So the last stage here that we want to talk about is optimizing inspection functions. So we talked about the process control and where we're just going to measure a single feature for the purpose of feeding back into the process. Because again, there's no reason to measure something that a machine can't cut. That's a waste of time out on the floor. But you do need to, your customers are not buying a part that has a single diameter of 4 inches. They're buying a complete assembly, or they're buying, a piston that has, all the features, or a knee joint that meets full fit, form, and function. So it is important that we do 100% inspection at some point in the process. So what we need to do there is optimize this. We can't be waiting in the example I gave before where we're waiting for feedback to come out on the shop floor. We can't afford the time to wait for the feedback to come manually from an inspection lab to control a process. However, periodically, we do need to check parts. When we're developing a new process, which is happening quite a bit these days, we need to prove out that that process is actually comprehensively producing a good part. So in this stage here, we want to do a comprehensive evaluation of the part periodically. Those measurements need to be traceable. And the traceability comes through an artifact or for calibration of the machine. That's really the benefit of a coordinate measurement machine in a company, is that's your traceable reference standard that you can use to check things, verify that measurement indeed correlates with all the other measurements taken around the world. So comprehensive evaluation of the part, traceable measurement, and we want it to be fast. We can't afford to wait to get information on what's going on with these parts. So even though we may not be using it directly for controlling tool or work offsets on a machine, we still don't want to be waiting long periods of time to find out what's going on comprehensively with the part we produce. The instruments need to be reprogrammable. There are many, many dedicated gauges that were built custom that exist in manufacturing around the world, but especially in the US. And these gauges, as soon as there's a design change, they are useless. And they're incredibly expensive devices to have when you are constantly innovating, which most industries these days are. So it's vitally important that the inspection functions are reprogrammable. And they need to provide a comprehensive data analysis so that you can look at different scenarios and really evaluate the cross effect of different, tooling methodologies and processing materials, things like that. So very comprehensive. So those are the critical steps for optimizing our inspection functions. So the best way to do this, again, if we're wanting to do this quickly, is to do it directly on the machine. I know this is a controversial subject. People many times, how can I measure on the same machine I cut on? Go back to step number one. If you have validated this machine up front and you've optimized its accuracy and you've verified it before you actually started doing your cutting, there's no reason why you can't measure directly on the machine. In this application right here, what we're doing is we're measuring a part. This is a graphical representation, but this part is for oil industry, a very expensive and a very heavy part. To move it off the machine, it takes a lot of effort to move this onto a CMM, a very expensive CMM. And also when you removed it, you've lost the reference to the machine. So it's really important that we measure this in process. So here we're showing software and probing system that can be used to measure that part directly on the machine. And so we showed very early in the process that we can use an artifact in the machine that we can validate right up front. This is a case where we would definitely want to have the machine compensated on installation. We would optimize its performance to make sure we have the absolute best positioning. And then we would verify prior to cutting. When we do this measurement, after the measurement, we would go back and verify that artifact. So now we've just proven, one, we know that we should have produced a good part because we had everything checked out in advance and the machine was capable and we set everything automatically and we had process control and all the elements that are in place there. But we go back and verify an artifact to make sure that all of the measurements that took place are indeed traceable and correct. So measuring directly on the machine is something that smart companies are doing, and it's something that I recommend that everyone look into to see where it makes sense. But there's times where it doesn't make sense. So if it doesn't make sense, what we need to do is make sure that we're able to do comprehensive measurement right out on the shop floor with minimal human interaction and, quite frankly, minimum number of different instruments. So we're showing here is a Renishaw system based on the Revo 5-axis platform. And this system, first off, allows you to scan out on the shop floor at speeds anywhere from 2 to as much as 50 times faster than traditional coordinate measure machines, surface speeds. But not only that, it allows you to select different sensors that can be automatically changed in and measure different attributes that would normally require different gauges. So in the top right there, you're seeing surface finish. Surface finish measurement historically is done with manual gauges, a lot of times in a lab for in-depth analysis, or with very rudimentary handheld gauges out on the floor that in some cases mark the part more than they measure the part. So when you measure on a device like a coordinate measurement machine, you're establishing the datum structure of the part first, so you know where the part is in space, and you're measuring the surface finish directly related to that datum structure. So if we look down in the bottom left here, I'll restart this again. If we can, the bottom left down here, you have a vision system. And so if you have 2D features, holes and the like that you need to measure for location, but they're too small to get a tactile element in there, a lot of times you need a vision system to measure those. So that can be tool changed in automatically as well. Bottom right down here, you have a 3D fringe structured light probe that can do a comprehensive analysis of the 3D topography of a part. And so all of these different things can be done on one instrument right out on the shop floor, right by the machine. So either measurement directly in the machine or measurement near the machine, full comprehensive analysis. What we want to do is try to optimize the performance that we get. So let's look at the benefits we get here. So first of all, from a flexibility standpoint, we are no longer going to be relying on dedicated instruments. Either the machine tool itself will be used or a device that's programmable out on the floor will be used that can manage many different measurements in one location. That provides the ultimate in flexibility. So we're able to reprogram that to be able to repurpose that device. So reprogram for the next part that you're currently building, but also repurpose that for the next design iteration that may come out. So the machine tool is adaptable and your devices that you use out on the shop floor are adaptable. Ultimate flexibility. Automation, so again, eliminating manual operation. It is very common for these dedicated gauges out on floors, on shop floors, to have people moving parts in and out of gauges, lots of manual operations, and not just the physical operation of loading the part, but also the data collection. So critical element of these devices is the ability to collect data and use that data to perform a comprehensive analysis of the part. And that data can be instantly shared electronically. So, you could be sitting in your office in France and evaluate your production in Mexico. In this day and age, we're automating not just the manual operations, but we're also automating the data collection and the ability to send that data out. So efficiency, we want to be able to buy these parts right off the floor. In other words, waiting for parts to be sorted by a quality inspection lab is very ineffective cost production. What we want to do is right at the source, right when that part is done, either on the machine or right by the side of the machine, when we need to do a comprehensive evaluation. And some industries can't get by with just a periodic check. The medical industry, in most cases, if something's going to be implanted in your body, 100% inspection. Aerospace industry, commercial products where an engine is involved and lives are in the air, 100% inspection is typically taking place on these. But in other industries, if you're looking at the body of a cell phone, or you're looking at a bearing that goes into a bicycle or something like that, you may be able to hold statistical process control and buy parts directly from the floor. Either way you do it, measurement on the machine, measurement near the machine, not moving parts long distances. And when the part is done and it leaves the area by the machine, it's ready for sale or ready to go to the next stage of your manufacturing operation for further processing. So in that case, it's going to its customer, which is the next stage of your operation. Final quote here from Winston Churchill. However beautiful the strategy, you should occasionally look at the results. So in this stage, you can have a perfect process where you optimize your machine, you verified it up front, you've removed all of your manual operations for setting, you've got closed loop controls, and beyond a shadow of a doubt that everything's perfect. You still need to verify. So having the ability to do a final comprehensive inspection is important. And folks, we are in a battle. We're in a battle to be able to keep up with the manufacturing output demands that consumers, both commercial and defense consumers have, and we have to do it with less and less people. And if we're going to go to battle, I want Winston Churchill at my back, okay? Because this is the type of thought process that we need to have going forward to make sure that we can be successful. So with that, I'm going to give you a quick view inside of Renishaw's manufacturing. And try not to focus too much on our products. These concepts can be used everywhere. But first off, always calibrating right up front. This is our own manufacturing, so we ball bar calibration. Now we're doing an inspection of an artifact on the machine, which is validating the machine. Then we're going to go ahead and set the tools. Automatically set tool length and diameter. Work pieces brought in, we're going to establish the location, set the work offsets directly on the machine. Again, no human interaction here at all. Commence cutting. Once we do our cutting, we can do some in-process checks on there. So making sure that our tool hasn't broken, because we want to make sure that if part is off, we don't want it to get into our production on down the road. But after we do this, we do a final check right on the machine, and those parts come off and they're ready for the next operation. So this process that we just went through, the production process pyramid, is a systematic approach that Renishaw developed, and the industrial metrology team and our team of engineers use this to assess manufacturing operations for our clients, our partners, and help people to achieve maximum productivity through a systematic approach of looking at their operations. And so with that, I would like to say that, with our team of engineers and salespeople and the industrial metrology team, we would really like to work with you to help you achieve flexible automated machining efficiency. This is a battle, and we need to work on this together. And I think the U.S. manufacturing industry is in a strong position. As we went through these, hopefully it gave you some ideas of things that you may be doing right, things that you might want to think about doing going forward. But I do wish each and every one of you tremendous success in your manufacturing operations. And at this point, I'd like to turn it back over to Michelle to open it up for questions. Michelle?
All right. Thanks so much, Dan, for providing those insights and offering the examples and just explaining the benefits of automating machining operations. As mentioned, we're going to go ahead and open it up for questions now. So if you haven't done so already, I just want to remind everyone that you can still submit questions by clicking the Q&A icon that you'll see there in your control panel. And we do have, it looks like, a few questions that came in, so we'll go ahead and kick those off. Dan, we have someone asking, how can these FAME imperatives help with Industry 4.0?
Oh, good question. So Industry 4.0 has, been a buzzword for several years now. And really, it's the phase of manufacturing operations where we are using cyber-connected systems. So we went from where we're using steam and power, which is Industry 1, to where we're doing assembly lines and such, Henry Ford, which was Industry 2. Industry 3 is automation and computer systems, which we're still in, and many companies really haven't even adapted to Industry 3. So a lot of things we're talking about are Industry 3. But Industry 4 is where we're using digital systems, simulation, information that we can share through electronic means to make decisions in advance of the mechanical operations. So how can this be used to support it is a good question. I wanted to kind of make sure everyone knew the state of what Industry 4 was first. But for Industry 4.0, it's really important to remember that at the end, when you simulate and you do all your digital transformations, you think of designs and optimizing things in artificial reality, you still need to produce a part because people don't drive virtual cars. People don't fly in virtual planes. I am not communicating with you on a virtual computer. These are things that have to be machined and made. So in the end, Industry 4.0's success comes from being able to convert all these digital ideas back into tangible parts and do it cost effectively. And my concern, quite frankly, is that we focus so much on the digitalization and the Industry 4.0 that we lose track of the fact that in the end, you still need to make something. So all of these imperatives that we're talking about here directly support the end result of Industry 4.0, which should be to more efficiently and effectively make novel, innovative ideas and products that people can use. Industry 4.0 is not an end game in itself, to be able to look at nice graphics on a screen. So with that being said, there's a tremendous value of Industry 4.0 and the data that you can collect in the process using the machine information, for example, understanding the machine capability up front, the information that's collected in the process so that you can look at, hey, what is my tool wear? Is this the effective feeds and speeds that I should be using because I've checked my form or my surface finish after a cut and I'm gonna dial this process in to make it better. So the feedback that you get from these processes is critical for people who want to engage in Industry 4.0. And quite frankly, it's used right now. So all of the applications that I showed, those devices output data that can be used in a connected digital world. And so I welcome the opportunity to work with people more on this, but I do want to make sure that people know that in the end, you still need to make something. And so don't get so hung up in simulation and digitalization. You forget in the end, you got to make something that people can touch, drive, fly, float, whatever.
Absolutely. All right, looks like we have another question here. Can probing systems be added to older machine tools?
Okay, good question. So yeah, most modern CNC controls have the ability to be retrofitted with probing systems. In fact, most modern machines coming out now come with the ability, either a probing system already supplied from the OEM or a very easy way to order it. But when you have an existing machine that's out there, Renishaw can do an assessment of that. If the machine has been built in the last 15 years, there's a high likelihood that a probe could be added to it. I would say if the machine is under CNC control and you're effectively using it, still making good parts, you have a very high likelihood of being able to put a probe on that. And that's a big portion of the business that, probing manufacturers like Renishaw have is installing probes after the fact on these machines. So yes, definitely.
Great. Okay, and then we have an audience member, they're interested in conducting an assessment. So they wanted to know, how can they get this done at their shop?
Well, you reach out to me, or if you have a contact directly at Renishaw already, any of the regional managers, and all the people within Renishaw. We're a very technical company, so we want to help our customers. We're about relationships. So if you want to reach out to me or your local Renishaw representative, the Industrial Metrology Group does assessments. We will go in and evaluate companies' manufacturing processes in accordance to the productive process pyramid principles that we talked about at the end, and give an assessment, an executive level assessment of areas where you're strong, areas where you're weak, and allow you to use that assessment to determine where you want to maybe make an investment in your people or your equipment to move forward. And keep in mind, most of the people who are engaged in this presentation are probably using some Renishaw products already. So again, I'll reiterate, yes, we're a manufacturer and we love to have people use our new technology, but we also want to take care of the people who already have our products. So if you're using our products and you see ways that you think, wow, I'd really like to apply that more in that direction, there's no charge for you to talk with us and for us to work with you, maybe give you some ideas of how you can use the products that you already own more effectively to achieve fame. So,
All right, perfect. That's very good to know.
okay.
All right, were there any other last minute questions that anyone from our audience wanted to send in before we close?
Michelle, while you're waiting for those questions, let me make just a note for people before we wrap up here. Over the next year, watch out my LinkedIn page. I will be putting up information. I plan on interviewing experts from different areas of industry. We did one for Modern Machine Shop a few weeks ago with Bob Sand, who is the president of Nelson Precision, which is one of the premier gauging manufacturers in the world, and kind of interviewed him and talked about the application of gauging and manufacturing. And we've got a series of experts lined up where I'm going to interview them, and then we'll walk through some of the concepts and principles that they've used over time to increase manufacturing efficiency. And I welcome people to chime in on that. And maybe one of you is interested in being involved in an interview with me. So if you are, please reach out via LinkedIn or through the email address here on the page.
All right, great. That's very exciting news. Definitely will keep an eye out for those. If there aren't any other questions, we will go ahead and wrap up. Dan, I want to send a special thank you to you for taking the time presenting on this topic. It was very insightful and informative, and I think our audience was able to take a lot away from it. And I also want to thank everyone who took the time to join us today. And we look forward to seeing you in the next IMTS conference sessions we have coming up. Hope everyone enjoys the rest of their day.
Thank you all. Appreciate your time.